You can find it online, so.
My computer's.
Okay, so we're going to deal with first 3 sections of chapter 10
Is there homework with this?
in our conversation about steel. There is. So, section 1, fairly easy, fairly straightforward, just talks about the major major types of steel that we use. So when we're talking about doing vertical construction with steel, what are the major size types that we use?
You talking about like not rebar, but
Not rebar.
Like I-beams and whatnot?
Yep, so yeah, so when we're doing steel frame construction, okay? Logan, what did you say?
What's an 18 wide web? I don't know. I thought that was one.
The wide webs?
Yeah.
Yep. And Steve makes a great distinction when we're talking about it from a structural standpoint. Yep. We're wanting these dimensions in our web and our flange to be fairly similar. Okay? It helps for, and one of the things that we'll look at is moment of inertia. That's what we'll look at for the homework. Okay, so we want our depth and our width to be roughly equal. Okay, so they're approximate. We don't have to have them be exactly equivalent, but the closer we get to a 1-to-1 ratio, the better off we'll be. Okay? We can also use round pipe. Oops. That 2 words.
you gave me a sheet pencil.
Dang, my pencil.
Okay, never mind. You're my go-to pencil then.
I won't give you any pencil more now.
And then rectangular members and or tubes. Okay, so those would be the big things that we'll think about when we're talking about structural steel. Okay, so the major force that you want to resist with your structural steel, what is it going to be?
Shear.
Bending. Compression.
Inertia.
Compression, right?
There you go. All of the above.
Now, but we bring up a very good argument. Compression is our major force, right? Remember that when we're talking about these structures, their primary purpose is picking up the load of the structure and transferring it down into the foundation, then into the earth, right? So the major portion that they're going to be doing is compression. But John, why did you say shear? Why do we need to be concerned about shear?
The bolts.
Yeah, we're going to have lateral loading going on throughout this system, right? They're going to be picking up load from floor joists. They're going to be picking up load from floor decks. There's going to be wind acting on this. There's going to be connections. So we have to take shear into account. And Rush, what did you say?
Bending.
Bending? Yep.
All your.
Now, when we talked about bending initially, we were talking about beams, right? Now we've taken our beam and we're putting it on end, and now we're talking about a column, okay? And what our bending becomes now, the terminology that we use for it is actually buckling. Okay? That's what we're concerned about. We're worried that if we don't have enough bending resistance, this beam is going to lose its shape and deform and buckle. Okay, and it's critical unfactored. I'll write down what table this was. I think it's table 10.2.
Is that it? Missed out on the grade science lecture, man.
I woke up this morning and didn't hate myself enough to come in.
Figure 10.3 on 336 gives you some visual aids of what buckling is going to look like. Okay? So that's what we're going to focus on predominantly when we're talking about this, we've already looked at compression. That's just our axial loading, right, that we looked at earlier in the semester. We haven't looked as much of how this bending translates into buckling. And so the first thing, if you're looking at figure 10.3, is how do we restrain these things and how is that going to impact our buckling? Okay, so we have a couple different end conditions. Okay, so the three conditions that we can look at are when we have rotation fixed, and translation fixed. Okay, so this beam is secured in a way that prohibits it from moving in the lateral direction. Okay, it cannot move in those directions. It's also being secured so that it's not able to rotate about that axis. Okay? So think of that as our, when we were talking about beams, remember when we talked about pinned connections? Okay, this would be like our pinned connections. Okay, we're not allowing it to rotate, we're not allowing it to translate. This up a little bit here. Okay, our next system is we're preventing it from translating, right? But because it's a simpler pin, this can rotate about that connection there. Okay, so we have 1 degree of freedom. Okay, and then our last system, which is going to be most similar to our roller connection,
Is both free?
rotation free and translation free. Yep.
Science.
Okay, very good. Deals with that end condition. Okay, so that addresses our end conditions. So now we need to figure out what our critical stress is going to be. Once we know what our critical stress is, we can determine how to size the steel. And this is going to be based on your, what the book defines as column slenderness. Okay, and so it's going to be the ratio of that length, okay, to its radius of gyration, how it's going to be able to rotate about those end conditions. Does that make sense? Okay? And what we look at is we need to figure out some sort of multiplicative factor. So if you're looking at figure 10.3, you have your theoretical K values, but then you have your values that you typically use for design. The values for design is what you'll typically use. And then you need to look at the ratio of your unbraced length to your
So what's K?
K is just, it's the constant value that you get out of the figure based on what your end condition. Okay?
So K is what we're trying to find.
No, so the question is K what we're trying to find? No. Based on what you know your end condition to be, you'll go to, you look up the table, here's what it is. Okay?
So K comes from a table.
K comes from a table. R comes from a table, okay? And the table that you'll need to reference is
10-3 on 336. Okay, I don't got my book.
what's that?
I don't got my book, don't I?
Yeah,
Well, 10.3 gives you your K value. Your radius of gyration is going to come out of Appendix 8.5, which is tables of properties of sections. And under 8.5, the section where the steel begins is page 649. Okay? And this is going to be dependent on the size of the steel, okay, the ratio of that distance to its length. What about our unbraced length? How would we find that?
Is that your depth?
It's not going to be our depth. It would kind of be given. But let's think about if we have a column, and here we have a connection to some sort of flooring, and here we have a flooring
Just the
here.
area that's not covered.
If this distance, we'll call it 20 feet, and it doesn't have any bracing, what is your unbraced length? 20 feet. Okay, so that's going to be provided in the homework.
So what I'm looking at right there is the width. Like you're looking at the beam like this way, right?
Yes, so if I rotate this
I would see the eye.
90 degrees towards you,
Okay,
you're seeing that.
okay.
Make sense?
Yep.
Okay. I guess you could be seeing too, I guess,
Either
that
way,
as well. It depends on what the total geometry of the structure is.
Yep.
Okay, so good question. Additionally, you'll need table 10.1. Table 10.1 gives unfactored compressive stresses for 50 KSI. Okay?
Is that the columns we're working with then?
Yep. Yep. For the homework that you'll do, you'll assume 50 KSI steel.
Okay.
Practically speaking, we want this value to have a range of 50 to 100. Okay?
This.
Our column slenderness, the value that we're
So
cranking out of here.
that formula should, if it needs to land between 50 and 100.
Yep. Yep. However, if you reference the steel code, 120 is about the practical limit that they give. Okay? If you get up close to 200, really bad things can start happening. Okay? Now you're starting to run the risk of getting into
So
buckle.
if we pop out an answer at 105, 110, it's okay.
Yeah, absolutely.
All right.
Absolutely. Yep. I wouldn't stress if you get out of this range. If you start getting above 120 though, then we should sharpen the pencil a little bit.
All right.
Lower limit? Or is 50
Like
that?
50, the absolute cutoff there.
So the problem that you're going to have if you start getting a slenderness below 50 is more a scale of economics. You're just putting in too much bracing, right? So you're either working an iron worker too much, or you're having the welders out doing too much work on the site.
So 50 is like that bottom limit?
Well, what if that's like what you come up with and it's okay though, like in that?
Yeah, it would be okay. Yeah, if you drop below this,
Like you're more than safe. Then,
Yep.
But like you're like, oh well,
Yep.
we need to fix this.
Now,
stuff.
yeah, now it-
stuff we do. Right?
Yep, exactly. Now we look into a thing of, hey, we should sharpen our pencil and see if we can provide a better design for the client.
Okay.
Okay? Then the last thing that we need is then to translate this into a safe axial load. Okay, and so 10.3 lays that out for us. Actually, is it all right if I erase this
Yeah.
for everybody? So I don't get too messy at the bottom of that board there. Okay, so determining, because remember, we still have to figure out, based on how this thing is going to resist buckling, we got to keep in mind that we're going to be talking about, we're going to be pushing compression through this thing too, right? So we need to figure out how to relate that buckling to what that compressive load that it's picking up, so we can run our check.
So it's a new, this isn't a continuation on this. Once we get that, this is a new problem?
Nope, so this will be the first step in
Okay.
getting to your axial compression.
Alright.
So this will be the last thing, and then we can start looking at some examples.
Okay, I just wanted to know if I do it in the page or not.
Okay, so we are interested in our ultimate load. Okay? And here, you can remember your phi sub c, okay, your compression factor is always going to be 0.9. Do be careful when you're reading through the text, when they set this equation up and they give you the 0.9 value,
Is that F prime C?
it's not F prime C, we're just dealing
Those
with
are all
steel.
subs then?
Yep,
Just
this is
everything
our
sub?
critical stress. It's our critical stress of steel.
You need to make that key, man. And A is,
A is going to be your area.
What's the
Okay.
sub, man?
That's your normal load that you're going to get from your buckling. Okay, so you don't need to worry about this. Okay, this is not the calculation you're going to make. This is the calculation you're going to make. Okay, your F primes, sorry, not F prime C, F sub C. Sorry, your critical stress comes from the table. Okay, once you calculate this. Okay? From table 1, what's this value?
what's C? That's compression, right?
Phi sub C,
Oh, 0.9.
0.9. Okay? Your area is coming out of the guide. Okay? Once you know what size column you're looking at, you just look it up. Here's what the area is. Okay? Seems straightforward enough?
How do you,
area-
so the area, I'm sorry, repeat that about the area again.
The area comes out of the appendix, appendix 8.5. So
Eight?
if
8?
8.5. Yep.
Is that 649?
649. Yep. I think I erased it.
I'm not
No, that's
seeing
cool.
anything else. It's right there next to the radius.
849.
8.5.
Page 649.
So drop down to page 649.
And PUs are safe
So,
load?
okay, so this is a stress.
Yep.
So what's its units?
KSF.
Pounds.
KSI or PSI, right?
Yep.
This is an area, what's its units?
Square,
Inches.
square feet, inches.
Square feet, square inches, right? So what is this thing cranking out?
Pounds per square inch or pounds per square feet?
Careful.
Pounds per foot? Kids per
PSI
foot?
here, right?
This pound, yeah.
Just
And we're
pounds.
multiplying by inches squared. So it comes out as pounds.
Yeah.
And we want an axial load, so that's a force. What are our forces in?
PSI. Pounds.
Our forces are in pounds, right? Okay? So dimensionally, we're good. Okay, so everything's gonna come out.
So. all right.
Kurt, getting back to your question. Brush, go ahead.
Nope, I'm just putting it together in my head, you're good. Well, yeah, how come OC? It was 0.9 and then, did you mean to write that up on top or is WC something different?
This is just, that's a typo in the book.
Okay. So do we need to worry with that?
No,
How does
no.
that even?
No. I just, as you're going through the book and you see this, you'll see this and you'll think, what in the heck is this? It's just a typo.
Alright.
It's supposed to be
It's supposed to be that.
phi sub c. So Kurt, if you go, so 649 is where it starts.
I was about to say, there's not a table on 649.
It's on 650. You're supposed to
Try the next
solve
one.
the
The next
shape.
one.
Use the formula of R.
So
Yep.
I mean, what's the B when you're
It's just a table.
Yeah, so, yeah, Terry, you're right. It does,
Oh, go
It's
ahead.
not
the
649.
appendix starts on 649. Your data starts on 651. Okay, so on 651 you have W shapes. Okay, it starts there. And your first item is your area. Okay, is what they give you.
And then little r is our radius of gyration.
Little I.
R under axis minus x.
Your little I value, go back to chapter 10.
And your radius of gyration.
Yep.
Okay.
Yeah, yeah, let's do the whole rest of the semester for you.
Do you have that?
Yeah, I think two instruction illustrations.
All equal to I over there.
Perfect.
Can't
Take
see.
yours first though. So you can, you have a little bit
I
of
just hope somebody thinks of us when it comes to.
administration final. What?
It's not Jay's fault.
No,
It's all these assholes.
no.
Oh.
What? I know, that's what I said, it's not your fault, man. These guys did us dirty. You are absolutely hilarious.
So, is the deal then, or what?
No.
What? Come on, Ben, tell us about my book.
Damn book.
You don't have one.
You say that now.
Do somewhere.
Man, I parked that book and I was so happy.
Put down in
about
my
it.
notes, Kurt, that it's 10.1, but it's not 10.1 when I look at 10.1.
For the unfactored stress.
Yeah.
I think Kurt's got one.
Good catch, Kurt.
I'm sitting
Good
here
catch.
trying to find this stuff and it's.
Yep.
So that's our negotiation, we could do that.
No, the old lady sister.
Okay, here we are. Yep, so then you need to go back to A.3.
That sounds bad, didn't it?
Which is not page 649, it is,
651?
yep,
And that gives you R.
It gives you the R all the way over, keep
Gives you
going.
two R's.
Oh yeah, there is two R's.
yep.
There's one.
So you're going to have an R sub X and an R sub Y. Okay, so it's going to depend about which axis you're looking. Okay, and so when you're looking at page 651,
As you can see here.
okay, your properties of W shapes.
X, R, X, X, Y, Y.
So we'll, yeah, I'm guessing I'll spell that out in our
So they're drawing,
Two sequence. R,
So,
okay,
Goes this way, or do we
So
go-
there's no table, it's 10.1.
there is a, yes, there is a table 10.1, that's where you get your critical stress.
so,
Once you've determined your K times L over R,
did we find that page number, or was that, are we not looking for that?
And why?
I thought we were just looking for 10.1 and it wasn't the right one.
Let's find out.
Yeah, isn't that what you just said?
once you determine this,
You literally just said that's not 10.1.
It is.
this value, you plug, you go and look through the chart on table 10.1, that gives you your unfactored compressive stress.
Which is K, or,
F sub C.
so once you figure out K, you correlate it to 10.1.
K times L over R.
Yeah,
Yep.
but you get K from 10.1, I thought.
You get K from 10.3, where it's got your end conditions.
Which is on the page.
336. Okay, I got it. So,
So I gotta go from 500 and something, 650 to 330.
Okay?
that, and that's the FC.
So yes,
Okay.
designing of steel is all about referencing tables,
Here's
okay?
3.1.
Moving back and forth between your tables.
So the safe axial load is the answer and
This
eventually
is what we
we're
want to
trying get.
calculate,
Okay,
right? Because what we're interested in, we're going to figure out the weight of our structure. How much load it's going to push through this steel. We're interested in knowing, okay, if we push this load through this steel, based on its end conditions, how is it going to try to bend? Okay? Now there are other things that we have to take into account. We have to take into account shear, we have to take into account torsion as well, but all that we're going to look at is we're just going to look at the buckling conditions. Okay? So, just like way back in the beginning of the semester when we were dealing with, you know, an 8-inch wood post, and it's so long, how much stress can it take, how much is it going to deform? There's a couple different ways that we can go about this problem, right? Obviously, if we know the weight of the building, we can plug this in, pick out our steel, and it can tell us this value, and then we can come back to figure out our unbraced length, okay? But some of the problems that you'll have is they'll have you figure this out, then move back and figure out what is your maximum load that you can put on your building, okay?
yeah.
So, sounds like it's as clear as mud currently. Should we look at an example problem?
Sure.
Yeah,
Okay.
best way to do it. is
They're
just-
number 1 on the assignment.
It's not going to be number 1 on the assignment.
I agree.
It's a good idea though.
I had to try that.
Yeah.
Yep.
Shoot your shot.
Perfect.
Okay, so we have
Do it.
a 12 by 53 flange.
I'm not going here.
No, no. Oh, no. That's, Does this one take up like a whole page, or am I good with that?
Yeah, you know what? Break out the new page just in case. Is that W for width?
It's a shape.
Or is that?
That's the shape. Wide flange. If you see W, you know that you've got a wide flange.
Oh, you do.
Okay?
You need to explain these things. A992.
Okay. I include this information just so you know some of the characteristics of it. A992 steel, or with a yield strength of 50 KSI, what we're going to be using, okay, this is a specification for this material. Okay, so it has to have a yield strength of at least 50 KSI, an ultimate strength of 65 KSI, and a 200 millimeter specimen has to have at least 18% elongation. Okay, so it has to be able to elongate 36 millimeters before it fractures. Okay? The other things that we know, our unbraced length equals 16 feet. Okay, remember that your unbraced length is your capital L. Okay?
So on that, then, when you give us our unbraced length, will you identify if it's?
Y or X.
Yeah. YY or
Yes.
XX?
Yes. Yeah, there won't be ambiguity as to if you're determining radius of gyration about the x-axis or the y-axis. There is the last problem that you'll have to do. You'll have to calculate about the x and the y.
Okay.
Okay?
I
So,
seriously don't even know what ambiguity is.
vagueness.
Okay, so No, so what I'm saying is that'll be given later. I thought it'd be part of the unbraced length, like, hey, the unbraced length is YY 16 feet. Fantastic.
Say that again?
No, no. We're just here to do the work.
What's your question?
Never mind. It'll be answered later, obviously.
Okay. So, our first step is, we know that we have, oops. 52 isn't a thing, sorry. 12 by 53.
Damn it.
Don't worry, it's not gonna ruin your problem. And we should stop a second. Does everybody, what does the 12 mean? Does everybody remember what the 12 means after the W?
Yeah, the height.
It's your, yep, it's your depth of your web, okay?
53 is the length.
Ooh, careful. What is our 53?
Pounds per foot.
53 is how much this thing weighs in pounds per foot,
Well, that's not bad.
okay?
I'm in the same class as you. Why don't you?
So I just don't like, cause like, wouldn't the unbraced be the same as the depth pretty much like all, like, I just don't.
So the question is, why is the unbraced length not the same as the depth?
Yeah.
So remember that when we're talking about the depth, now we're looking at this thing, it's coming out of the board at us and it's going back into the other room. Our unbraced length is, remember that we're making a column out of this thing, right? It's not going to do well as a column if we're placing it this way, right? It's going to be acting as a beam. So now we're going to rotate this thing, and I don't know, are we just rotating it 90 degrees, or are we rotating 90 degrees and then 90 degrees this way? It's going to depend on the structural geometry.
Height, unbraced length.
Okay.
You know what I mean? Running it long ways, that's the unbraced length, and here would be the I.
Yeah.
It's like having a two
That'd be
by
the height.
five.
He's,
Yeah.
Yes, exactly. Yep. Yep.
okay.
Just draw I-beam on that.
What's that?
Just draw
Yeah,
I-beam on it.
yeah.
There's the height. and
Yeah,
on top.
this would, yeah, very true. This would be your unbraced length running along here. Here's
Gotcha.
your depth. Okay?
You gotta dumb it down for us there, Ben.
It's making sure we're all on the same page.
Yeah.
What?
Statics for dummies.
That's what this book should be called.
That's some
Okay, so
Really read that book.
let's hop down to 8.3. So get down into the 650s in your book. We got to find W12 by 53 so we can figure out our properties.
In the middle is 653.
Okay, so what do we know about W12 by 53? What's its area?
15.6.
15.6 square inches. What is Rx? Its radius of gyration about the x-axis.
Well, how do we know it's the x-axis? What is the y-axis?
Cause he
He's
said
asking
so.
for the X, dude.
Because I asked you for the x.
Okay, what if you don't ask us that?
Don't worry, I will. I'll do my best to not let you down, John. Okay?
I'm very let down that we're doing this.
Yeah, I was gonna say, you
Yeah.
already, you
Well-
already let me down.
Well,
I didn't even come with my book.
5.23. What's Ry? Our radius of gyration about our y-axis.
2.48.
So what are we,
2.48.
what are the units?
What do you say?
Sorry,
Inches.
inches, yes. Thank you, Rush. Okay? When we are talking about our columns, which of these do you think is going to govern? Just at the onset. You got a 50-50 shot.
RX.
Think about,
Damn it.
oops. Think about the equation. Okay? If we're not going to change this, right?
The length, yeah.
We're not going to change the unbraced length. We're just changing how we're looking at this thing,
That's an end condition.
right?
RY.
We're not going to change our end conditions, right? 'Cause we're not going to change how we pin this thing or how we fix it into place. Right? Which of these do you think is going to govern? Which of these do you think is going to be more critical to us?
No clue.
Which one's Y?
RY is 2.48, the smaller number. RX is 5.23.
RY
It's
is
the larger.
critical.
Why do you think?
It's smaller.
Smaller number. Yep.
Why is, okay, what, just, never mind.
It's okay. It's okay.
Nope, I'm good.
Is there a visual?
Point to
that you
Y
can-
and X on that I-beam.
On this I-beam,
Yeah. Where's RY and RX? Whatever the hell that thing is.
So you're saying
Very nice.
that Y is 2.4 inches long, and the RX, it's
I thought
the
this was
width
the,
is 5.23.
no, isn't that the allowable rotation?
that's the, so. I'm trying to think of how much time we should take on radius of gyration.
No, you know what?
So-
Listen, move on.
Radius of gyration is going to give you, as you load this thing, and it's starting to bend, okay, the radius of that bending as it's rotating, what
Okay.
that dimension is.
Okay, I thought it was actual.
It doesn't have anything to do with actual physical dimensions of
Dimension.
the steel.
Okay, that's what I thought I was looking at.
It has everything to do with as this thing is being compressed and it starts to rotate, the measurement of that rotation.
Okay.
Okay? Yes, Marcia?
So so no matter what, like regardless of, is RY gonna always be smaller than RX or can it be?
That's a good question. I did not do steel design on a consistent basis. I believe, off the top of my head, if you're dealing with flanges where your width is essentially the same as your depth, your R sub Y should be smaller.
And is that always gonna, so is the small one always the more
The smaller one,
important one? Right?
generally speaking, is going to be what drives your maximum factor.
So that's the one where, so we're always gonna look for RY to what to put in for our equation.
Generally speaking, yes. Yeah, unless you're specifically asked to determine it for both dimensions, okay? Because again, remember, if we're in a situation where our column, where we do not have close to a 1-to-1 ratio, then we're definitely going to be interested in doing that calculation. Okay, that's a good question. Okay, so our column then will be unbraced on both ends.
I'm just trying to think. Is Y smaller? It's easier to bend it that way.
And so we haven't been provided, since we know that it's unbraced on both ends, we are not given an express end condition. Okay?
Because we can't have the people.
So what should we do? You want to go to 10.3 where you get your ranges of your different dimensions. Your conservative value, if you don't know an end condition, is to assume that you're going to have pinned, where you're going to resist translation, but not rotation, okay? So you're going to use a K factor of 1.
So that one came off of a chart?
Yep, that's from figure 10.3. No, not out of here. Comes from
336.
figure 10.3. This guy.
Yeah, 336, right?
Oh, I'm sorry, is 336 what you said?
Yeah, page 336.
Okay, yes, sorry, 336. Yep.
About to fight it.
Okay, so calculate your relative slenderness, K times L divided by R. So what's our K value?
One?
What's our L?
16.
16.
Feet.
What's our R?
2.48
So you divide,
0.48.
inches.
So times the feet.
Are we happy,
No,
or do we have an issue?
Yeah.
times 16 times 12.
To 192 instead of 60.
Or do you need it, yeah.
Huh?
Can you go either way, convert feet to inches, inches to feet?
You should get these into inches to use the table that the book provides you. The book has it in inches over inches. Okay? Well, no, think about this now. No, it's not gonna matter. If you've got feet to feet, your ratio is gonna be the same. Okay? So,
But the next step that would matter, is that all in inches?
the next step.
Yeah, when we're doing the.
Because that gives you your FC.
Well, in your next step, you're just using your area, and you're just going to use a critical unfactored stress that you just get out of the table.
For the safe.
And the number that comes out of the table is in PSI.
Okay.
Okay? So. So what does this end up being? 77.4?
Yeah.
Okay. Typically speaking, when you're working with your relative slenderness, just round it to the nearest whole number. Okay?
So 77.
So this guy just becomes
77?
77. Okay? If we were dealing with, whatever, 16 feet 4 inches, whatever it takes to push this thing to 77.6, then just round it up to 78. Okay? That's all that we need to do.
Yeah.
Make sense to everybody?
Yeah.
Okay?
And we're in the.
So now, reference table 10.1.
I don't think it's in anything, I think it's just 77. It's not, there's no like, inches or anything, it's just 77.
This is a dimensionless factor.
Yeah.
Yep,
Because they cancel out.
yep. It's,
32.
instead of relative slenderness, it's also known as slenderness ratio. Okay? You have a ratio of inches to inches. So,
Steps down.
so I mean, I guess technically, Terry, if you're interested in what the units are, it's inches per inch. But,
So that gives us what?
so, jump onto table 10.1. So you have you have 6 columns there, jumping across. Columns 1, 3, and 5 is your relative slenderness, your K times L over R. Okay? Columns 2, 4, and 6 are your unfactored compressive stresses. Okay, so you find where your number is in columns 1, 3, and 5. It's going to give you a corresponding unfactored compressive stress. So for KL over R of 77, what's our unfactored stress?
32.4.
32.4.
Where do we get the area?
Table 10.1, page 337.
651. Page 651, ain't it?
No, 337.
For A? Your area?
No, for
that
the
number.
unfactored.
Yeah, I'm beyond that. I'm looking for the area.
We found it already.
We already have the area.
Yeah,
It's one.
that's what I said.
15.6 inches.
That's on page
You guys pay attention,
651.
man. I'm just lost with all my book, man. Answering shit I don't need.
Okay? But this is an unfactored stress, okay? So we have to figure out what's a safe load. So that's where we need to get back to
455.
Damn it.
0.9
0.9
times 32.4
times 32.4.
inch. Or
KSI.
KSI.
Times
15.6.
our area, 15.6 square inches. Okay?
455.
$455 kips. Okay? So,
Skips.
what happens to this number if we plug in 5.23?
It's gonna be smaller.
It's going to be a smaller number, and so what does that mean for our unfactored compressive strength? If we have a smaller number,
It's only 10:45.
okay, so at 77 we have 32.4 kips. This guy drops down to, let's see, so that would be about 5, so it's going to drop down to about, we're about halving it, roughly, right?
So it will be at like 220.
So we'll say 38 for our slenderness. 38 gives you an unfactored stress of 45 KSI. Okay? If we plug 45 KSI in here, does our number go up or does our number go down? It goes up. Okay? But we need to make sure in making our recommendation that
You get the lowest.
we get the lowest value. Okay?
Alright.
That is going to be the most conservative. Because if we make a recommendation and say, hey, it's great, you guys are you're rotating about the x-axis, you can take on whatever this ends up being, 800 kips. I didn't calculate it out. We'll just say that.
630.
What's that?
630.
630? Okay. And this thing gets built, and it gets built in a way where they're actually rotating about the y-axis. What is going to happen?
Florida.
It's probably not going to remain a building, right? It's going to become a pile of scrap. You probably won't get called back to redo the work. See if-
Direct
The labor
process.
side of it would.
What's that?
The labor side of it.
Yes, there is, yes, that is a good point. There is more work that has to be done. It's probably not the firm that made this recommendation that's redoing that work. Okay? Does that make sense,
Yep.
generally speaking? Okay?
Sure.
We got like one of these for homework then?
What's that?
Got like one problem for homework?
Well, I've got another example if you want to look at it, just to kind of confirm everything and make sure that we're on the same page.
Let's do it.
So we got 455 kips is our answer.
405, yep. We're looking for computing the maximum factored load. That's what this guy is here. Okay? Yep.
So wouldn't it be the minimum?
The minimum would be the maximum that you would want to do.
It's the maximum that you want to exert on that
Oh,
column.
okay. Yeah, I got
Yep.
it.
Yep. It's the minimum that it can take based on its orientation. But it's a, think of this as,
Yeah.
if we use the definition of the maximum as a do not exceed, that's a great question, Rush, is what are we talking about when we're saying maximum here? Yep.
I got you.
Okay.
We were talking earlier about that 50 to 100 to 120 number. Was that slenderness or unfactored slenderness?
That guy.
Thank you.
Also a good point. So Kurt just asked, when we talked about that 50 to 100 range, what is that number?
Okay.
That's our slenderness, okay? So yep. So here we're at 77, so
with that,
we're happy with
so
that.
with the 5 point, when you use 5.23, then that would be literally too much bracing.
Yeah, what it's telling you is you don't have to
We're
hold back
overdoing
at 16 feet on brace.
We'd be overdoing it.
Yep,
At
Yep. yep, exactly. All very good points.
Damn, brah.
Okay, so we will still have a 12 by 53 flange. We're still going to have yield strength of 50 KSI. Okay, so we will also keep. I need to erase that. We'll keep a 16-foot unbraced length. And I suppose then we didn't need to. Our area will remain the same, right? Because we're using the same.
So we're just changing
System.
the R and Y.
No, our X and RY will be the same. Because we're using the same beam. We're going to change the end conditions. Okay?
Okay.
Okay? So this time, instead of making an assumption about the end conditions, we're going to pin the top, and we're going to fix the bottom. Okay, so how this will look, this is how our end conditions are going to look, okay? We've pinned our top, okay, so it can't translate, but it can rotate, okay? Down here, can't translate, can't rotate, okay? If you look at 10.3, what does that give you for your K value?
10.3 was on.
Use the one below. The theoretical isn't what we use. Use the lower values. 0.8. Yep.
So use recommended.
Yep. Use the recommended, not the theoretical.
Okay.
Okay. So slenderness. What do we need to calculate here? Our slenderness is our K times L over R, right? Yep. Yeah, here all we've done is change our K value. And what do we have to remember to do here?
Amplify inches.
Multiply by, I guess I should say multiply by 12 inches. Get it so that it's dimensionally the same, right? Okay, so what do you get for a slenderness?
62.
62.
And that's unitless. That's just, hey, we're between 50 and 100.
Yep.
Right? Okay.
Yep.
37.7?
What?
Sorry, never mind.
What's
Did you
that?
forget to?
Oh, you're looking at the, yes, looking at the unfactored.
Got you pointed.
Yep. Yep. And as Kurt said, this gives us an unfactored load of 37.7 KSI.
So we put that into.
Right, so then we plug that into our ultimate load equation, right, where we have phi sub c times s sub c times area. Okay, so here we have 0.9 times 37.7 times 15.6. Okay, our 37.7 is in KSI,
529.6.
our 15.6 is in inches squared. And what'd you say, 529 you got? Yep.
Yeah. Now that answer is going to be whatever it's going to be, as long as our critical is between the 50 and 100. We just plug it in, and that's just. There's nothing like, oh, we went over, or we need to redesign it. That's good.
Yep.
All right, cool.
Yep.
So any of the ending situations you're going to give us, we can find on this.
Yes,
Right.
yeah. You won't get an end condition that isn't covered by that
Okay.
table. Yeah,
I
it's,
can do that.
how would you be able to find it, right? Got it?
So I'm just making sure there's an answer to all the problems you'd like to do. Seems to be a running problem in this class.
Typically. There's one problem on one homework.
No. Hell no, there's been a few. There's been three.
There's
It's
three?
been three. Now you can counter back and say two. I'll disagree at that.
We'll split the difference and say one.
I'll go back. I think there's one.
We can talk about it offline, sure, I'm willing to talk about it.
Because we found one in the example. And
Oh,
then
and
another one
yes.
you said we don't have enough information.
Yeah, yeah,
So we're already up to 2. You want, let's keep pushing this to 3, 'cause I'm pretty sure there was 3.
okay. So, we'll look at one more example. Here we're going to have differential bracing on both of our axes. Okay, so the last problem that we looked at, we had an unbraced length that was the same in both dimensions. Okay, and so for this one, we don't know exactly what we're dealing with, but some sort of multi-floor construction. Okay, and we have, oops, sorry, this should go like this. Okay, so we don't know what's going on with these connections. We don't need them at this point for our calculation. But keep in mind that if I tilt this thing down to you, right, I rotate it 90 degrees, I should check the picture. Let's see.
So
I just want to make sure that I have the right unbraced
if you
length. for the
tilt
right
that
drawing.
towards us at 90 degrees,
So if I take this
You got it from the top, make it 8.
and I pull it down,
then we're gonna be looking at the,
Oh, this one.
yep,
okay.
yep. So now you're looking at this thing. Now it's coming in and out of the board.
Yeah.
Just so I can show you
Yeah, okay.
what's going on here. Okay. So we have to keep in mind this is going to make for different unbraced lengths, right? Because these are going to act as braces in this dimension. Does that make sense to everybody?
Wait a minute. So the top drawing is the view of the bottom drawing? Or the? Okay.
Does that help? Here we're looking in plan, here we're looking in elevation.
Bird's eye.
Did you say that?
Yeah.
Cool.
Yeah. Want to go on a date after this or something? Alright.
I'm just going to, even if that's planned, I'm looking over the top. If I'm looking at the
You're not
elevation of
seeing-
it,
you're not- There you go.
that makes more sense.
Does that help?
Yep,
Okay.
okay.
So, as we're looking along this axis, we're going to have a brace length of that length, right?
Mhm.
This is going to act as bracing along this axis. Does it act as bracing along this axis?
No.
It does not brace this thing at all. So then we need to know what that distance is. That's what that unbraced length will be. Does that difference make sense to everybody?
No.
Okay.
Isn't it gonna be the same?
Why do you think it would be the same?
I mean, unless you're having a different elevation of the floor heights, then wouldn't it be the same?
Okay, so think about what we're looking at here. We're looking at buckling, which is bending stress, right? If I try to bend this thing like this, are these going to do anything to brace it?
No.
Or are they going to simply rotate along with it?
Rotate.
Rotate.
They're just going to rotate along with it, right? If I take this and try to bend it like this,
Then they'll do something.
they'll brace it, right? They'll be providing bracing, okay? So your unbraced length then is going to be whatever that length is about this axis.
For X,
Yep. Your unbraced length, let's call them L1 and L2, right? Is going to be your unbraced length when you're looking about this radius of gyration. Okay? Do I have your buy-in?
I mean, I believe you. I just don't.
You just don't believe me?
No, I just don't fucking get it.